Before watching this lecture, you should have a pretty good understanding of the AR1 process, the autoregressive process of order 1. This process will be generalized in this lecture into the ARP process. So here is the definition of the ARP process. We say that this time series process will follow a stationary ARP process if the process itself is stationary and if it's the case that yt is determined according to this model. So yt is equal to a constant beta 1 plus another constant times its lagged value yt minus 1. That part was included also in the AR1 process. For the general ARP process, we go further than just one step back. So we also include as an explanatory variable the y variable lagged twice. So yt minus 2, and that has a parameter of rho 2. And this goes all the way to yt minus p periods back in time. And finally we have the error term. So you can see that the AR1 process is indeed a special case of the ARP process. It's just the ARP process with p equal to 1. In most cases, the error process of an ARP process, the epsilon t terms, are assumed to follow a white noise process. And the definition here of a white noise is exactly the same as in the AR1 case. That is, all the error terms need to be independent of all lagged values of y. They need to have expected value of 0 for all t, and they need to have a constant variance of sigma square for all t. So this process is a little bit more complex than the AR1 process. Here we have a direct effects going back further in time, but some general ideas that were developed from the AR1 process are still applicable. First of all, whether this process satisfies the stationary condition or not. Now remember the AR1 process, we had the important stability condition, which stated that the rho parameter need to be between -1 and 1 strictly, and that was a necessary condition for stationarity. Any rho value outside this interval must lead to non-stationarity of the AR1 process. It turns out that there are similar stability conditions for the ARP process, but unfortunately they are not as simple to state. And since this is just an introduction to the AR1 process, all we do here is simply to claim that stability conditions do exist for the ARP process, and they are all in terms of these rho parameters. Just like for the AR1 case, the stability condition is a necessary condition for stationarity of the ARP process. Second, we also discussed the moments of the AR1 process. We said that, okay, suppose that the stability condition is satisfied, that the rho is strictly between -1 and 1, then the necessary condition for stationarity is satisfied, and based on that, then it's actually possible to find the moments of yt. We could find the expected value, the variance, and the covariances. Turns out that you can actually do the same for an ARP process, but again, the answer is a little bit more complex. So if you have a stationary process and the error process is white noise, then it's possible to find expressions for the expected value and the variance and the covariances. These will all depend on the unknown parameters beta 1, rho 1 through rho p and the sigma square. The final topic we discussed for the AR1 process was the estimation of the unknown parameters, and we found out that it is possible to estimate the parameters consistently even though Gauss-Markov isn't satisfied. And the same will actually be for the ARP model, as it is stated here. As long as the process is stationary and the errors are white noise, then the OLS estimator will be consistent and the standard errors will be consistent as well. Estimation of the ARP process is therefore really straightforward, and it can be done in any econometrics software simply using the linear regression feature.